Hey AP, in this video we're going to talk about titrations and titration curves. So a titration we have done in chemistry, and we usually do it with vinegar and sodium hydroxide. And we have a setup where we use an Erlenmeyer flask. And the reason we use an Erlenmeyer flask is because we want to prevent splash out when we're adding our titrant to our analyte. We usually set this up with a ring stand. The ring comes out with a burette clamp, and then this thing here is a burette. And the burette, we will notice, has large numbers at the bottom, let's say 50 milliliters at the bottom, small numbers at the top. And we look at the change in volume that we use. So we always record where we start, where we end, which is down here, and we look at the change in volume that we've used to figure out what we have. So we talk about final minus initial to figure out how much volume we used of our titrant. So some of these terms here might be new. And first is that a titration is a controlled addition of a titrant used to determine the concentration of an unknown solution. So the titrant is what goes into the burette, and we see that here. This is our titrant, the solution in our burette. And we put that in our burette because the titrant is the solution of known concentration. We know the concentration of that. And we use a titrant to analyze our analyte. And the analyte is the solution of unknown concentration. Our analyte goes in our Erlenmeyer flask, and this is what we are analyzing. So we analyze the analyte. Notice that this is the same. Okay, we analyze the analyte because it's an unknown concentration. So we use our titrant to help us determine the concentration of our unknown solution, which is our analyte. And in order to know that we have made it to neutralization, or we've made it to the point where our hydrogen ions equal our hydroxide ions, we put something called an indicator into our analyte. In the past, we've used phenolphthalein because that turns pink in a basic solution, because we start with an acid down here of vinegar, and then we put phenolphthalein in and it stays clear. And then as we add in our base, our sodium hydroxide, that turns pink. And once it turns a really light pink, we know that we've reached this neutralization point where our hydrogen ions equal our hydroxide ions. So the point where an indicator changes colors is known as the end point. And an indicator, that is a weak acid or base that changes color when the pH changes. So that's an indicator. And it's a weak acid, and this also is a weak base too. So, and we'll talk more about those in an upcoming video. The equivalence point is where there are equal amounts of both hydrogen ions and hydroxide ions. Okay, and that means that if our hydrogen and hydroxide ions are equal, that means that we have a neutral solution. When we're doing a titration, we are looking at an acid, HA, which is our acid, reacting with our base, usually some sort of BOH. It doesn't have to be an OH, right? We can have things that are like ammonium, right? And they are always going to react together, especially if this is a strong acid with a strong base. They're always going to react together to make an ionic compound, which we call a salt, and water. And we say that this is a neutralization. Oops, that's wrong. Neutralization reaction. Because we're neutralizing our acid and our base together. And depending upon if we start with a strong acid and a strong base, well, those will totally neutralize each other. However, if we use a weak acid and a strong base, or a strong acid with a weak base, I'm going to sneeze. I don't want to. Then we're going to have our point of neutralization is going to be, slightly acidic or slightly basic, because depending upon what's strong and what's weak. So we're going to take a look at those. The other thing to note is that other things that react like bases are ammonia compounds, NH 3 compounds. Sometimes you'll see, or also like amines, and amines is things that ends in like NH2. This nitrogen hydrogen group likes to receive a hydrogen, so it acts like a base. So just be aware, sometimes you'll see things that end in like NH2, and those are bases because they're receiving hydrogens. So we can plot and graph these curves that we make from titrations. We will have our analyte added. That is the thing we can control. So that goes on the x-axis. And then what's dependent upon that is our pH. And so our pH goes on the y-axis. So as we are adding titrant to our analyte, we are measuring the amount of titrant that we are putting in. And then we use some sort of indicator, whether it's a universal indicator or a pH paper or a pH meter, to measure our pH. We can also do calculations to figure out what the pHs would be based on the different volumes of titrant added. And that's what our next video will be on, is how do we do these calculations so we don't have to do the titration. But so long as we know concentrations, we can plot what this curve's going to look like. So here we have the titration of 25 milliliters of a 0.1 molar HCl with 0.1 molar sodium hydroxide. Again, HCl is a strong acid, NaOH is a strong base. So our overall net ionic, our reaction that we have is we have HCl plus NaOH and strong acid, strong base, so it's a one-sided arrow, is going to make sodium chloride and water, which we can write as HOH since we pulled the hydrogen in the hydroxide. Well, strong acid, strong base, completely soluble in water, so totally ionizes or dissociates into its ions. Sodium chloride also dissociates into ions because it's a group 1 salt, so that's completely soluble. And then we're left with water. Water is a liquid, so that doesn't break apart. So my overall reaction for a strong acid, strong base is our hydrogen ions plus our hydroxide ions make water, H2O. So that's our overall reaction. In our curve here, we will see that we are slowly increasing the pH. So we start with all acid, right? We're titrating 250 or 25 mils of a 0.1 molar HCl. So we start with our acid. This is all acidic. This is our acid of HCl. That's all we start with. And we are slowly adding in sodium hydroxide. So at the beginning, we're slowly starting to neutralize our hydrogen ions, and the pH slowly starts to go. And then all of a sudden we get to this point where we shoot up. And at the point of inflection on this vertical line, which is somewhere about here, this point of inflection, which is where we go from a positive slope to a negative slope, that is where we have our equivalence point. And for a strong acid with a strong base, that equivalence point is at a pH equal to 7, okay, because our strong acid completely gets neutralized by our strong base. Okay. However, if I have a weak acid and a strong base, well, I'm going to have this strong base is going to overpower my weak acid. So if I have a weak acid, HA, generically, with my strong base, and strong base is hydroxide, they are going to make, when they come together, H2O and its anion of A minus. Okay, that's going to be floating around in solution. So then we need to look at, well, what does this anion do in solution? How does that impact our overall reaction? So specifically for this, we have 0.1 molar ethanoic acid, which is also another name for acetic acid, with sodium hydroxide. So we have acetic acid, HC2H3O2, plus sodium hydroxide, NaOH, okay, weak acid with a strong base. So we're going to have some sort of equilibrium will end up being established. Sodium and the hydrogen swap places. So I'm going to get NaC2H3O2, and I'm going to have my water, H2O. And we just said that, well, this guy, right, sodium hydroxide is totally ionized. So is this. That means really the sodium isn't going to be sticking around with this, right? It's going to break apart. It's a soluble salt. So that's going to go away. And really we'll just have our strong base as just OH, because that sodium is really just a spectator ion, so we don't need to include it in our solution. So really, once we have these two interacting, we now have this situation where my anion here, my conjugate base, because it's lost the hydrogen, is going to do some reacting with water. So my conjugate base, C2H3O2 minus, with water, well, that is going to want to grab my hydrogen from water, HC2H3O2, and then it's going to leave hydroxide ions floating around in solution. So in my solution, I'm going to have these hydroxide ions floating around, which is going to cause my equivalence point, even though it's fully reacted, I'm still going to have hydroxide ions floating around, which causes my equivalence point to be greater than 7. And we see that here as I start with, right, this is weak acid that I'm starting with, and I'm adding strong base. So I start to creep up in my curve, and then all of a sudden I hit this point where I spike up, and the point of inflection is about here. So that's my equivalence point, but we can see that because I have a weak base present, and therefore hydroxide ions present, right? Here's my weak base, reacting with water is going to leave hydroxide ions present. That means that my pH is going to end up being greater than 7 at that equivalence point. Similarly, with a strong acid and a weak base, we're going to end up with hydrogen ions present, and a pH at the equivalence point is going to be less than 7. So if we take a look here, we have HCl with ammonia. So ammonia is NH3 reacting with HCl. So when ammonia is going to grab onto that hydrogen ion, so we're going to have NH4 plus, and then we're going to have Cl minus. Okay, so those are those reacting together. And this ammonia, okay, this weak base, or sorry, this weak, conjugate acid here, is going to interact with the water in the solution. So we're going to have our NH4 ions are going to interact with water. And because it's a conjugate acid, it's going to donate that hydrogen ion to the water. So we're going to have NH3, and then we're going to have H3O plus. This guy is our hydrogen ions, so that's going to cause this to be slightly acidic. So if we look on our curve here, well, we're starting with, let's see, this curve, titrating HCl. So we're titrating a strong acid. So here we've got strong acid, and we're titrating it with ammonia. So we're adding in ammonia, so that's why the pH is going up. We can see that my equivalence point here, right, is definitely less than 7. So my equivalence point, because now I've got a weak acid, right, my conjugate acid, my weak acid, and that's going to create hydronium ions in my solution, which means that my pH now is less than 7. So you can see that here. Now, if we have a weak acid and a weak base, and we want to figure out, well, how are these going to interact? That's where we have to start looking at Ka values, because it really can vary what the pH is going to be at that equivalence point. For this example here, we have ethanoic acid, which is acetic acid, so HC2H3O2, and then reacting with ammonia, NH3. Two weak acids, or a weak acid and a weak base, so we're going to get C2H3O2 minus, and we're going to get NH4 plus. And then we'll have to see, well, how does this reaction, and looking at, how does this react with water? What does it make? Looking at the hydrogen ions that we have and hydroxide ions that we have in solution here. Looking at the hydrogen ions we end up in solution here and seeing, well, what has a bigger impact on our overall pH? But just know that for here, my pH at the equivalence point is going to vary depending on which weak acid and weak base that we have and their strengths, like how weak are they, or maybe they're a stronger weak acid or weak base. Okay, so we'll continue to analyze these in a POGL tomorrow. The other thing that we can look at more closely is this equivalence point. So we just said that it's located in the point of inflection of the vertical portion of the titration curve. Important to note that if I have an acid, so a polyprotic acid with multiple hydrogens, okay, so let's say that this guy had multiple hydrogens, maybe it was, or maybe a better example would be like this one, like if I used sulfuric acid instead of hydrochloric acid, I would have one of these straight lines for every hydrogen that I lost. So if I had a polyprotic acid with, let's say, 2 hydrogens, its curve, if I started, would be like this, and then it would come up again, and then it would look like that. So I'd have multiple points of equivalence in my curve for every hydrogen that I had removed from my acid. And we'll see that these start to get smaller, but still, they're still going to have equivalence point. Again, we see this using indicators. Indicator is a weak acid or a weak base, where both the ionized and unionized forms are going to have different colors. And an endpoint is an observable change of color. So some different indicators that we have. We could use methyl orange. That starts as red in an acid and turns yellow in a base, and it has a pH change of about 5.6. Methyl red goes from red in an acid again to yellow in a base. However, it has a pH change that's a little bit more basic. Still acidic, still on the acidic end, but a little less acidic than my methyl orange. Litmus paper. Red litmus paper goes from red in an acid to blue in a base. And that happens a little bit higher than 7, so maybe the 7 to 8 range. And then phenolphthalein is colorless in an acid and pink in a base. So something to note about litmus, we can have red litmus paper turns to blue. So red paper that turns to blue, that's a base. And if I have blue litmus paper that turns to red, it's an acid. So red to blue base, blue to red acid. When we're trying to determine what indicator we want to use, we want to choose the indicator that has an endpoint, which is the pH color change. This is our endpoint. We want that to be about the same as our equivalence point. So that way we know that that's where that vertical line should be in our curves. Well, let's take a look at some of the math that we can do with titrations. So during a titration, a titrant is added to an analyte until the new solution reaches an equivalence point. When a strong acid and strong base are titrated, they will neutralize each other at the equivalence point, which will be at a pH of 7. Okay. So if I'm looking at strong acid, strong base calculations, all I need to do is stoichiometry to figure out how many moles of acid get neutralized by how many moles of base, and then I can figure out my concentrations, pHs, and so forth from there. So what is the concentration of phosphoric acid? Phosphoric acid comes from phosphate, H3PO4, if it's neutralized by 20 milliliters of a 0.2 molar sodium hydroxide, NaOH. So if I know my volume of my base added, and I'm trying to figure out the concentration of my phosphoric acid, well, this is like I've already calculated and grabbed the data. I've gathered data from doing a titration. Now I'm just plugging it in. So first thing I want to do is write out my reaction. So H3PO4 reacting with sodium hydroxide. Okay. The hydrogen and sodium are swap places. So I'm going to get Na3PO4. And I'm going to write water as HOH just because it's easier to balance that way. 3 hydrogens, 1 hydrogen, so I'm going to put the 3 there. 1 phosphate, 1 phosphate. 1 sodium, 3 sodiums, so I need a 3 there. It gives me 3 hydroxides, 3 hydroxides. So I am starting with, so I'm using 20 milliliters of a 0.2 molar sodium hydroxide. So I have 20 milliliters of a 0.2 molar sodium hydroxide. And I have 10 milliliters of some molarity of my phosphoric acid. Because I know the stoichiometry, I can then go ahead and figure out what this concentration is just by doing stoich. So starting with what I'm given, my 0.0200 liters of sodium hydroxide. And I have a concentration of 0.2 moles of sodium hydroxide for every 1 liter of sodium hydroxide. And I want to figure out moles of acid, right? Because this is molarity. So I want to know moles per liter. I know my volume already because I have my 10 mils, but I want to know my moles. And this is neutralized. So, right, so it says neutralized here. So that means that moles of hydrogen are going to equal moles of hydroxide. So I need to figure out, well, how many moles do I have of this guy to neutralize this one? So for my reaction, it takes 3 moles of sodium hydroxide for every 1 mole of phosphoric acid. When I do my math across and divide by the bottom, I get 0.00133 moles of phosphoric acid. So I know my moles. I'm going to divide that by my volume of 0.0100 liters, and I'm going to get 0.133 molar H3PO4. So figuring out my concentration, I need to know moles, I know volume, I know what I'm neutralizing it with. So if it's a neutralization reaction, I can just use my stoichiometry. So we'll practice more of these in class tomorrow.